Hello, everybody. Thank you for joining us again. This is our 7th webinar now we've been doing with RAT's technical sessions. Today we have a topic on steam turbines, controllers specifically. So anyways, thanks everybody that's joining here. Quite a few people obviously from Edmonton and Alberta, but also a lot of people I've seen in Germany and Qatar, and also India, Malaysia, Kuwait as well, and India, a lot of people from the States. So anyways, we appreciate you joining us. Also one from the UK, I see. So thank you again. So I just want to mention here, I'm going to try and pull this up on the sharing screen. Let's see if this works. Well, the link is going to be on LinkedIn and on the slideshow presentation as well. But in essence, there's links to the past technical sessions if you want to see some recordings, and also there's also the archives of our past MRO conferences from 2014, 2016, 2018. Well, you'll be able to see some of the presentations there if you're interested. So in any case, the other thing I want to mention too is that we do have a couple scholarships that we've provided now for 2020, and these are for Red Deer College. So Trevor Newfield, electrical engineering technology, oh, sorry about that, and Dexter Tatry, also from Red Deer College, industrial mechanics. So congratulations to them. I'm hoping maybe we'll just have a little online presentation for them sometime in the future. So with that, I'm going to hand over to Ralph. He's going to introduce our couple speakers for today, and we'll get started.
Yeah, thank you, Andrew. My name is Ralph Dickow, and I'm looking after selecting the presentations and with help from Andrew. And also, well, I'll just jump right into thanking you for joining us today. There will be a survey question at the end of this presentation I'd like you to reply to. There's opportunity to ask questions throughout the presentation. Just go to your control panel there and click on questions, and we'll get to a Q&A at the end of our presentation portion. Starting off will be Rame Isbate, and he's currently with the Alberta Governor Services as Sales Account Manager. Covers Saskatchewan, Manitoba, and Alberta. He's been doing this for the last couple of years, helping customers to find the right solutions for control systems for rotating equipment. He has over 12 years of experience in rotating equipment, including gas turbines, steam turbines, compressors, and pumps. And following Rami will be Ashraf Abdul Rahman, and he has 15 years experience designing and integrating turbine control systems and machine monitoring systems. He has excellent cross-functional and cross-border cooperation skills, strong focus on assisting delivering quality products and ensuring customer satisfaction. He has a master's degree in mechatronic engineering and is Green Belt certified. So thank you to our speakers this morning, and let's begin.
Hi everyone, thanks for joining us today. My name is Rami Isbaita. This is my second year with Alberta Governor. I have more than 12 years in rotating equipment. I'm my friend Ashraf. Ashraf actually is leading the engineering division at Madsen. I know many of you now is asking how come we coming from two different companies. Actually, Alberta Governor Services part from Madsen Group. So how it works, we are the Alberta Governor is the distributor for Woodward in West Canada. Madsen is the distributor for Woodward in East Canada. So actually together we cover the country coast to coast, and of course we work together as sister companies. Now, before I hand over the microphone to Ashraf, we raised one question. We hope everyone can answer it, which is simply is how often do you or frequently do you you tune or calibrate your turbine controller after commissioning? If there's any question, we would love to hear your feedback on this question. And without any further delay, I give it to Ashraf. Ashraf, please, you can begin now.
Okay,
Yes,
so far, we have a quarter of the people, 25% of people have voted so far. So we're watching the numbers trickle in.
okay.
And after, well, we might give it another 30 seconds, I guess.
So I'm going to give a quick introduction about myself during this time. So my name is Ashraf Abdurrahman. I've been working with Madsen now for 5 years. We are the Woodward representative in Canada. Woodward is 1870 company. So we started in 1870s. We started with designing governors for hydro applications. And now we are in 2020 and we are doing aircraft engineering. We are doing so many things within Woodward. And we are the representative in Canada. And today I will be happy to discuss with you one of the patents that Woodward has made. It's about adaptive PID tuning. I think we've shared that patent in our LinkedIn account, and you can able to see that patent in here. And basically this presentation is all about how we are doing that adaptive PID tuning. So without further ado, can we see the result of the poll right now?
Yes, that'd be perfect time for that. And so here we are. Seems like most people are doing it after an overhaul, basically. 58% of people. Surprisingly, 21% have never tuned their controller, and 5% say once a month, and 11% say once a year. So seems like most people after a major overhaul, it seems to make sense to retune or recalibrate your controller at that point. So I'll shut down the poll and continue on.
Okay, thank you very much. Thank you. So this is not a surprising value that most of the people does the tuning of their PIDs after major overhaul. But today I'm going to discuss a little bit about the issues that we face with tuning of these controllers, and we're going to go through them. And after that, we will have a lot of discussion probably about, yes, we need to do it frequently, not frequently, and so on and so forth. So I think by the end of the session, we'll be a little bit more understanding about what we are calling adaptive PID tuning. Because using adaptive PID tuning, you can able to do it as frequently as you want. Not like back in the old days where you are afraid to do it manually. But let's go through the presentation, and then after the end of the presentation, we will be able to understand it and understand how easy it is to do PID tuning nowadays, so that you can able not to do it just every major overhaul. You can do it whenever you start to see any performance changes within your turbine. So conventionally speaking, usually as a user, you have 3 types of PID parameters that you are controlling: the proportional, the integral, and the derivative. And if you use only the proportional, what you will gain is you will have reached to your target, but with a steady state error. So basically, if your target is to reach to an RPM that's 3,600, you will reach to 3,400 with a steady state error. To reduce that error, we introduce the integral, and the integral is being used to make you reach as possible to the error. But the problem with the integral, it sometimes causes some delays, overshoot within the system, and that's where the derivative comes in to improve the delays, so you can able to improve the delays within your turbine. For example, I am just going to give a quick example that we can able to look into it and see how it's working. We have here an application where we have an engine with a speed control, with a PID controller. As you can see, that engine is behaving unstable. You can see that there is a huge error coming out of it, and there is instability within the system. So to improve the stability of the system, you start to tune the PIDs or use the PIDs. Right now, the proportional is 1, so it's not almost nothing. So if you start to choose the PID, which is the proportional, start to reduce it, and you will see here that the performance of the system start to improve a little bit. But you still have that error. So basically the system here, it's an engine that required to change the speed from 2000 RPM to 3000 RPM. But because of the proportional error alone, you still have that steady state error. Of course, in the normal application, this is just a simulation. The steady state error would be much more smaller, but this is an example of what is the proportional gain do to you. It's just allow you to reach to the system, but you still have the steady state error. To reduce that error, as we discussed, we need to have the integral gain added. So I'm gonna just change the integral. Now I put the integral into effects. Instead of 0, I'm gonna put it with a value here, 0.01. And I will run my simulation again. Now we reach to the desired effect that we're looking for. Depending upon how aggressive your system is, sometimes customers, they use their steam turbine in applications like frequency control, where they need to control the frequency of the whole grid. And sometimes that delay between the actual speed that they are looking for and the controller or the turbine to reach that effect, that delay makes a big difference for them. So we can introduce at that time the derivative term, which I will introduce in right now. And you can start to see that the system will start to become more aggressive to reach to its objective, but you will have faster response out of the turbine itself. So as you can see here, the turbine response becomes, the aggressiveness is there, that reduce a little bit the overshoot, and you have more stable turbines. So typically, a commissioning engineer will go to the site, will spend maybe days or 1 or 2 days till he can figure out, okay, what are the values that I need? What are the values that I need so that I can able to control my turbine? What are the values that I need so that I can able to achieve my objective, basically? And to achieve this objective, usually what we provide or what we need as control engineers is to know the system, to understand the behavior of the turbine, to understand the behavior of the final control element, which is usually an actuator or a governor. So to understand all of these parameters and their effect on your system, we have to understand what can cause instability in my system. I finish my turbine, I commission it, and then I have instability. What are the reasons why this instability? Why we need to retune our turbine every couple of years, every performance behavior changes. Usually, as the turbine get older, you start to have, this is an example for a typical steam turbine governor, where you will have a hydraulic, electro to hydraulic valve, and then you will have a pilot valve, and then you will have the steam valve itself that controls the opening and the closing of the steam and allowing the steam to go to the turbine. If you look at them, you may face so many mechanical issues. One of them is the sticking of the governor valve. The other is also the linkage. So the linkage between the governors and between the joints in here. All of this, as the turbine goes older and older and older, these linkages start to wear out and start to have some issues. You need to accommodate for these issues within their controller, especially as the turbine gets older. Okay, there is another type of valves which we call them poppet valve, which is like 6 or 7 valves, and each one open, allowing a certain amount of steam to come in. So as these poppet valves start to get rotten or get worn out, also you have some instability coming in. Again, you have what we call a pilot valve in the middle. If this pilot valve also start to stick, you will still have some issues within your turbine. The steam valve itself, so the valve seat itself start to get older and older and allow more steam to come in. This is something that might happen during the engineering stage, that you incorrectly selected or sized the actuators or sized the valves. So you have some inherent problems that you need to accommodate while you are tuning your system, is that the valve itself incorrectly being sized. So you have to accommodate for that while you are tuning. of course, the steam conditions. So usually when you first commission your turbine, you run it at a certain inlet and exhaust pressure values. And then eventually the process gets bigger and the boiler gets older. You start to have different header pressures. Changing in the inlet and the exhaust pressure affects also the performance of your turbine, especially if you're using your turbine to control your exhaust. And then last but not least is the hydraulic pressure that goes to the valve itself. If there is any impurities in the hydraulic pressure, all of this causes instability within your turbine, and we need to accommodate for that. So within the patent itself, there is a mention for the study being conducted on sites, on the plants. And it was found out that 68% of the controllers out of 150,000 controllers loop was not performing as acceptable as it was supposed to be. It was performing actually unacceptable. And out of this 65, 15%, like out of the 30% that was, or 42% that was performing good, is that only 15% was performing at optimum conditions. 15% was performing at optimum conditions. So that tells me that usually the turbine owners and users don't intentionally want to compromise on the performance of their turbines and their processes, but because of reasons that the control loops and the reasons that we discussed in here tends to run out by time and by usage, customer will need to retune his turbine a little bit so that it allows for these conditions to be compromised within the controller itself. And to understand how to tune a PID, or to understand how the tuning of the PIDs of the turbine is challenging, I have here two examples of two types of PIDs. This is a typical example, which we call it a parallel PID. And that's usually used within gas turbines, where you will have the speed in parallel with the acceleration PIDs, in parallel with the inlet temperature, in parallel with the exhaust, in parallel with the acceleration PID. All of these PIDs goes together, and the lowest value from these PIDs will be sent to the actuator so that he will allow more fuel to go to the turbine or less fuel to go to the turbine. So if there is any problem with tuning is of any one of these PIDs, it will definitely impact the stability of the whole system. And then if you can able to isolate which PID that you have the problem with, you need to make sure that that PID, when you tune it, it performs within the required customer needs. So parallel PID is the way that we currently use for gas turbines, and tuning that and retuning it required an excessive engineer with a lot of experience who understand the other PIDs and the impact of changing one PID, making one PID more aggressive than the other PID, and understand how the different modes of operation of the turbine itself and the requirement of each mode. In compromises, or in the opposite direction, there is the series PIDs, which is typical within the steam turbines, where you will see this, for example, a cascade PID or a load PID is controlling another PID, which is the speed PID. Usually the speed PID needs to be more faster in response to the cascade PID, so that whatever changes required by the cascade PID, the speed PID will be able to do it. And sometimes with the parallel PID philosophy, you have what we call a ratio limiter, which basically takes into the account the speed PID and the exhaust PID. Both of them goes together to what we call a ratio limiter to account for, okay, if the speed PID asks for 50% and the exhaust PID asks for 40%, they goes through an equation and says to the HP valve within the steam turbine to open that amount, or the LP valve to open another amount. And as you can see, it's a complicated PID, one PID affecting another PID. Both has to be working together in coherence so that you don't have one PID unstable and the other PID stable, and it affect the overall performance of the turbine. Usually customers, we prefer to use the speed PID or the series PIDs in steam turbines because it allows us to control the minimum and the maximum process limit. So I can able to say, for example, I don't want my turbine to go above this value or below this value because this is the maximum value that I can reach with my turbine. or in case I lost, for example, the speed set point, or I lost some critical value like the pressure input, I can able to maintain the last value and I can able to control that. So that's why people prefer to use the series PID rather than the parallel PID. But as you can see, these are all kind of challenges that people need to understand when they are trying to tune a PID or trying to choose how the PID should react with the other PID. And to be able to solve all these issues, we use different methods in industry. So one of the methods, we call it Ziegler-Nicholas method, which basically depend upon you have a step change, you connect it to the system, and based on the response of the system, like how much it took for the system to respond, you start to calculate the proportional, the integral, and the derivative value, the one that we see. And typically, if there is a table for the Ziegler-Nicholas method, if you follow the table and you can able to tune your turbine based on that, you will start to see that the behavior of the turbine will be attenuated. So for example, the first overshoot will be, for example, 1%. And then the next overshoot or the next step or the next cycle, you will see that there is attenuation by 1/4 of the previous one, and then 1/4 and 1/4. So if you follow the Ziegler or the typical Ziegler-Nicholas method, this is one way of tuning your turbine so that you can optimize, you can reach the actual stable condition that you look for. And you can also, during the transient state, you see that the turbine performance behave as required, as intended to. It's not only the only method that we use for tuning the PIDs. We use different other methods. We may use a method called Cohen-Kuhn method to tune the PIDs. All these methods are being designed so that depending upon what is the response that you require from your turbine, that method is being used. So in Ziegler-Nicholas method, we usually use that with the turbine that don't have a lot of dead time. You don't have a lot of response time from the turbine. So in hydro application, I don't recommend using something like Ziegler-Nicholas method. In steam turbine application, yes, you can use Ziegler-Nicholas method so that you can tune your PIDs. So in reality, the tuning of the PID required a lot of experience, required a lot of understanding about the typical response time of the turbine, required typical understanding of the system gains, like what are the gains within the system that you are trying to control, require understanding upon the process itself. For example, some customer has processes like when you try to control the kilowatt or try to control the frequency, well, the process requirements are very aggressive. So you need to tune your turbine aggressively so that you can achieve that high frequency response or high response of the system. Or you have a pressure or a temperature process where you are trying to tune it slowly a little bit so that you don't have this aggressive responses. Because if you have a lot of aggressive responses within your turbine will cause disturbance within the system and will cause issues within the system. Also, that you have to also understand the mechanical portion of the turbine, the actuator itself. What are the non-linearity? For example, poppet valves have non-linearity. They are, yes, 10, 20, 30, but these valves are not non-linear. All this is a criteria that you have to consider when you are tuning your turbine, that you may have some non-linearity in the valve so that you are at 20%, and then when you start to open or to ask for the turbine to open to 25, you get a more response out of the turbine. So that needs to be accommodated also in your tuning so that you can able to accommodate for these changes. We talked about a little bit about multi-loops and PIDs, and each PID is trying to communicate with the other PID. So that was in the previous slides. This is also, all these parameters has to be considered when you are tuning your turbine. And in some cases, I'm not able to tune it or take it to the maximum conditions. I cannot, to tune it, you need sometimes to take the turbine to instability so that you see what is the maximum range that you can take your turbine at. And sometimes in the site, you cannot able to reach that level. So to do that, you have to always have that experience. It takes years of experience to go through it, but it's what we are doing every day. One more thing that also impacts the tuning of the PID is how fast is your controller. For example, if you are using an analog controller, the analog controllers are very quick to respond to changes within the inputs. But if you are using digital controllers, if the digital controller cycle time, by means of cycle time, we mean that the time it takes you from receiving the input and the controller calculating the action and then sending the output to the actuator or to the final control element. If it takes 5 milliseconds, you may have like 1.05, as you can see here in this graph. You will have a little bit overshoot within the turbine. The more the controller cycle time takes, the more that you have, or the more the controller time it required to be able to take an action, the more you can able to see overshoots. And that is basically outside of your capability, because the controller itself needs 100 milliseconds to take an action. And in some cases, this 100 milliseconds can cause serious damage, especially if you are talking about a steam turbine application, where usually people design the turbine to be in serious damage if you go maximum above the maximum governor speed by 1.2%, which is 120%. So if I want to reach to the maximum governor speed and my controller go above the maximum governor speed by 120%, this will cause a serious damage and you may damage your turbine. Usually when we go and set up our trip limits for this turbine, we set up at 1.1%. So you need a fast acting controller in some cases, especially if you are talking about the generator application, if you are talking about loading or unloading application. All this application requires a fast acting a controller that can able to give you a response within accurate time. And now we are going to go for the solution. Our solution that we have been talking about and this patent is about using adaptive PID tuning. Basically, the adaptive PID tuning, I'm going to show you an example for it right now, where we basically, what we do is this is in here, it's in front of you, you see the graphs for a steam turbine controller where you are trying to tune. When you see the blue line at this level, it means that the adaptive PID tuning is working. When you see at this level, the adaptive PID tuning is off, it's completed its calculation. And this is the actuator output. And this is the speed changes. And this is the speed set point that we are trying to achieve in here. So in this application, customer is usually has used the adaptive PID tuning a couple of times. So he was able to achieve a very nice performance out of his turbine. And this is where we did the first adaptive PID tuning and we start to see the behavior changes. So I'm going to zoom in so that you can able to see what we actually do with the adaptive PID tuning. So the moment we enable our adaptive PID tuning in our controllers, what we do is we do step changes. This step changes in the actuator. So we open the valve and close the valve, open the valve and close the valve in cycles. And the controller calculate how much is the response time from opening the valve till we start to see changes within the speeds. And we use a combination between Ziegler-Nicholas method, the one that we discussed earlier, and the Cohen-Cullen method, so that we can able to achieve what we call an opti-tune controller or opti-tune response. So as you can see in here, we do a couple of these steps at different time zones and different dead times. And based on the calculation that we do, we come up with a new proportional, integral, and derivative values. And when we check the different, and then the customer will have the ability to see the difference between the old values and the new values, and can able to decide, okay, let me tune the turbine, let me change these values or not. And as you can see, by using the adaptive PID tuning, we will able to achieve our targets in here. So if you see the error, just a second, please. So if you look into here at the speed set points, so if you would like to see the changes within the speed set point, so this is the set point right now, which is around 4,890. And this is the maximum value that we reach, 4,889 RPM. That's the maximum RPM that we reach to. And this was able to be achieved with this low changes is basically due to the ability of the adaptive PID tuning to reach to the best steady state point for the unit itself. You can also achieve that manually, but that will take hours and hours and hours, and it may take a long time for you to achieve it. Adaptive PID technology is been there in the market for a long time. People have used different methods for it. One of the methods is actually connecting your controller inputs and outputs to another software on the or another PC on the outside, and that software will calculate, or we do what we call learning. And basically what it does, it will calculate how much is proportional, integral, and derivative. But by experience, it was found that there are so many issues basically related to when I do that learning curve, I need to make sure that the scaling of the input and the output is the same. That the controller itself have been, or the machine itself have been in different scenarios, so that it can able to learn properly. Otherwise, it will give you values based only on the scenarios that it has been through it. But if you have the controller itself built inside the controller, the PID or the adaptive PID tuning, what you will have is that the scaling and all this intricacy, all this calculation is done internally within the controller. It's not exported to outside devices, and it's more convenient for the operator to do it. It's more easier for the operator to do it. So basically, the adaptive PID tuning allows you to control your turbine or optimize the performance within your turbine within the controller. You don't have to use an outside devices so that you can able to identify or decide which P and I and D value you are used. And as of the publication of this paper, we have been using this adaptive PID tuning in all our turbines, almost over 1,000 turbine controllers globally. And we have been seeing a very positive results coming from our customers that tell us that, okay, the PID tuning has helped us to do a lot of tuning and help us to improve our performance and the process and the stability of the unit itself.
Yeah, Ashraf, it's 12:32.
Okay, thank you very much. Thank you. So typical when you have a turbine with a manual or typical PID responses, you'll start to see that, okay, with the manual control, you will start to see that you have one rise and then we have another 1/4 rise. So this is a typical response that you can see in many turbines in the market. And you can see how the valve changes, opening and closing, opening and closing. And yes, manual control allow him at the end of the day to reach to what he wants, to stable, but you can see how the valve has been opened and how he used his valve and affected his valve opening. So when you use an optimized PID tuning, or when we use an OptiTune capability or adaptive PID tuning, you will reach to your optimum performance, because as you can see, it's very hard to do these step changes, the one that we represented earlier. Manually, it's done on a computer base, like it's done on in the controller itself. So these steps are being done by the controller, and the controller have some safety in it. So if case, for example, if one of these steps causes disturbance within the environment, it will quit the changes and will back to the old unit values. So we have tons of fail safeguards to allow to the operator, to allow to the team to tune their turbine without having any issues, worrying about instability happen within the system or instability happen within the turbine itself while doing that tuning. But when you do it manually, sometimes the turbine goes out of control, then you have to shut down and impact the process itself. But when we do it with automatic control, the automatic control will take a quick response to avoid any imbalance or instability within the turbine. So going back to the presentation, so if you can see here, we have two examples where we have the OptiTune being used, and as you can see that the valve itself has not been opened too much, so you have overall stability, which is way more better. You will have the valve opening is way more less, and you have improved the overall process stability and end user quality. And you didn't use the valve, you didn't not damage your valve, but didn't consume a lot of your valve, because you can see here the valve has been open, closed, open, closed. It makes difference over the years and years and years of using that valve. We reduced the commissioning time. So before it was an engineer who sits down with the operators and they go and tune the value and wait for the system to be stable, then put another value and wait for the system to be stable. By using an OptiTune or adaptive PID tuning, we have consolidated all these experiences, and we have used less time for commissioning of the turbine due to that. And the convenience of just pressing a button within your controller itself, so that whenever you see any disturbance is good. It's excellent. Now that you have just a button to press, you don't require a lot of training as it used to be. In the past, you go and you have to train the operator to understand the difference between the 5 PIDs. And if you play with this PID, you may cause instability for the other PID, or you can cause another issue with the turbine PID. So now you don't have to go through that. Using the adaptive PID tuning, all you have to do is just to press a button, and that will take care of that. You don't have to train people to understand how the other PIDs are working and go through these dynamics. Increase safety, because the adaptive PID tuning has its limits. The moment it starts to see that tuning of the turbine causes disturbance, it will quit the adaptive PID tuning. It will tell you, no, we cannot continue on doing that, because right now we are disturbing the process. So if you start to, if the controller itself start to see that, okay, we going above a certain boundary for disturbance within the system, where the adaptive PID tuning will quit. And this is how it looks like from our controller here, is that you can see that we have that's the speed PID, we have the load PID, and we have the calculation being done. So basically it will tell you, okay, what's the speed right now on the turbine? What is the test sequence that's going on? So you can see here, for example, we have enabled the PID, and then the analysis steps has been done. It goes through these steps and do the calculation. And if it failed, or if there is an issue that prevented from tuning, it will give you an alarm or tell you exactly what the problem is. Maybe the inputs that I am asking from the turbine itself, I'm asking too aggressive. I'm asking it to aggressively try to tune the turbine. So that's an issue. So in order for you to be able to tune your turbine without having an issue, these will tell you. And then you will get the values for the proportional integral. This is the old values, and this is the new values. And based on, if you see the differences and you like what you've seen, you can just say, go ahead and run the new adaptive PID parameters that you can able to calculate. In the end, we have been using it. We have been improving the performance for our customer. We have lowering the operating and maintenance costs. We have improved the plant safety. And this is one of the testimony from our customers telling us how the adaptive PID tuning has helped him to optimize his turbine. And it didn't require a lot of training to use. It has improved his reliability, it has reduced his maintenance cost, and it has improved his plant safety. Yes, and this is the end of my presentation. If we can go ahead and someone has any question, go ahead and let me know.
Yeah, actually, so QL Sani had a question, whether the PID tuning is certified for SIL 3.
Yes, we are using it in our SIL 3 applications, adaptive PID tuning. So we have applications where we have already installed this SIL 3 solutions, and it's been used and it has been certified for SIL 3.
Okay, thank you. Well, if there's any other questions, you can either...
I have some questions, actually, if I can, Ashraf.
Yes,
you showed the module there. Is that panel mounted or is it portable? And I guess with that, does it need to be, is it wired in to existing controller instrumentation, or exactly how does it interface with what's there already if you came into a plant to install this?
So the adaptive PID tuning is already installed in the software, in the hardware itself. So that we can get the values. So if you look at that, that's actually the controller itself. And it comes with the software built in with the adaptive PID tuning, so it can control the turbine and can provide the adaptive PID tuning. It's built in inside, so that all the sensors, reading, everything is already being connected to the unit itself, so that it can able to do the calculation and can able to generate the output that we are looking for.
Where this controllers doesn't exist right now, do you actually have to install it, and do you have to add more new instrumentation? And I guess that question goes with, will it apply to both electronic and analog controlled turbines?
So what we usually do is we replace the analog controllers with this controller. So this 505 turbine controller or micronet turbine controller comes in built in with this adaptive PID tuning. It's more as a software piece rather than a hardware piece. So it's not like an external controller that you add to. It's actually built inside our controller itself, the adaptive PID tuning.
Is it suitable, Ashraf, with anyone's turbine, or is it only work with one that has existing Woodward system?
So it's suitable with the steam turbine. We have it installed in any type of steam turbines. We have it installed in gas turbines, and we have it installed in sill-free applications where it required adaptive PID tuning. So it's basically a software piece that we added to our controllers itself, so that it allows it to be able to reach or to tune the unit itself.
Mm-hmm.
So you see this is actually taken from our controller itself. This adaptive PID tuning is actually part of our controller itself. You can see how it's done, and it's included in the controller itself.
Do you require a new instrumentation or additional instruments to be added to have the feedback that you need for this controller to function properly?
No. Just the speed and whatever parameter. For example, if you are controlling the pressure, you already have the pressure already as an input. We can use that. Whatever you want to control itself, it will have that unit itself. So we don't require the special instrumentation or new instrumentation for it.
Okay, so we have a few other questions. Keywall, I think I've unmuted you, so if you'd like to pose your questions. Ashraf?
Oh, okay, Andrew, so the question is regarding GE frame 7. We have frame 7s at our site, and I was wondering if because it has Mach 6 control, how your adaptive PID control works with the GE.
So we have our own what we call micronet controllers. So we replace we actually work with GE turbines to provide them with controllers. So one of our biggest customer in the market is actually GE, and we actually sell them our micronet controller with built-in adaptive PID tunings installed directly inside them, not as a separate entity. It's basically inside it. So we replaced the old Mark 7 or Mark 6, sorry, with our own micronet, and we can able to do the adaptive PID tuning for frame 7 controllers, basically.
So how many gas turbines you have done so far on frame 7?
With Woodward, probably hundreds. I can check for you, but I don't have the numbers in front of my hand. But yes, we have done it with frame 7 because we are the biggest supplier for controllers for GE frame 7.
Thank you.
No problem.
Okay, so we have a question from Doug Barr. He is asking if you've got sticky components, how does the PID help to control that or resolve that situation?
So, sorry, can you
if
repeat
you
again the
have
question?
sticky valves and sticky valve stems and whatnot, how's the PID act to control that?
So in a sticky valve condition, depending upon how severe the sticky valve is, our controller will go and try to tune the turbine. And if it's couldn't able to tune it, it will give you like an alarm and fail and tell you that the process variables or the process gains in the system itself is beyond the ability of because at the end of the day, the valve itself has to be able to perform. If the valve cannot perform well, then it will tell you that it failed. But if the sticky is something that is like happens and very small, and it can be able to accommodate for, like the controller can accommodate for it, so it will do that and will give you the new parameters and new values.
Okay, very good. So Jerry Kidd had a question as well. So basically, since what year or what date the 505 has been standard with this adaptive controller feature?
So this patent was introduced in 2017. This is introduced in the latest 505 controllers, the new ones. So they can easily be replaced. So if you have an old 505 controller and you want to replace it with a new 505, it's plug and play, and it's easily to be replaced. We even have the old wiring of the old 505 can be connected to the new 505. So it's very easy to do the upgrade or to change it. But it's within 2016 we started to have this adaptive PID tuning installed in our controllers.
Okay, so I'm assuming you'd have to shut down the turbine then to disconnect and replace the controllers. Yeah.
Exactly.
Yeah. And so that's not available on your P200s, correct?
No, it's available under P200. It's in the
Okay.
P200.
Okay. Yeah, that would have been useful. Back in 2006, I remember helping to tune a Peak 150 at what used to be Next in Long Lake. Well, CNOC now, but yeah, I remember, that was 14 years ago, but I do remember having to, just manually play with it and try to get the response of the system. It took pretty much all day to try and get it tuned. It was tricky. So.
Yeah, and that's what we are trying to say, that manual tuning can be achievable, but it takes longer to achieve. But with the adaptive PID tuning, you don't have that time. And basically, it allows even the operator, after you left the plant, like after we finish the tuning and we finish, and then it happens that you have a big load changes or something like that, and nobody was there from us. The operator can go and hit a button, and then he can do the recalculation, and then it can calculate, and then can able to tune the turbine. And the performance of the turbine goes from instability to stability again, and he can continue on without disturbing the process a lot.
Yeah, that's really good. There's so many benefits, like you mentioned. I mean, just the longevity of your components, right? Makes a big difference.
Exactly.
Well, I don't know if there's any other questions from the field out there. We've got a little bit of time left, so.
Oh, maybe I'll ask the question. Just for Ashraf, how long does it take if this has not been installed to actually adapt it to put it in and get it all set up? I'm assuming there's some modeling required so that it knows exactly what PNIDs are inputting into the control of the turbine. So how much time does that require?
So what it does is basically we have 3 different modes. We have either with proportional integral, and proportional and derivative. And usually you run it with the proportional alone and see the responses of the turbine. Then you run it with the proportional integral and the proportional derivative. And usually each mode itself, it takes 10 to 15 minutes. So maybe half an hour, 1 hour.
Oh dear, looks like we may have lost.
Oh yeah. Yeah, it looks like he's frozen there. Okay, well, I guess that might conclude our presentation. I mean, if there are any other questions, you've got an opportunity in the survey or on LinkedIn as well in the group or on our company page. you can always interact on the post for this presentation.
Here's an attachment as well.
There is, yeah, the handout, that is the presentation itself in a PDF format, sorry. So feel free to download that. And also, of course, this recording will be available afterwards as well. So I guess I just want to just take a brief moment here. This is actually good timing because I'd meant to just recognize our sponsors that have been able to make this and all our past events possible. When we used to meet at Polo's Social Lounge, and before that at the New Asian Village, all the food and drink was provided for by our sponsors. Oh, hi, Ashraf.
Sorry, guys, I got disconnected here. I'm sorry, back online.
So I was just, mentioning, so, these are our sponsors that, help us with all our costs. And, it's been a partnership for, probably about 16 years, I guess now, for a lot of them. So anyway, Ashraf, did you have any other closing words?
No, I think that's okay. If Rami has anything else from my side, I'm good to go now. And guys, I'm available. This is my email address. If anyone has any question after the presentation, can you see my screen right now? Is it still working?
Oh no, sorry. It looks like I must have taken back.
Sorry. No issues.
I can do that here.
Okay. Yes. So right now you can see my screen right now. This is my email address. This is contact details. In case people would have any other questions or looking for solutions or something like that for tuning their turbines, for making their turbines performance improve, please give us a call and we are available here to help you as much as we can.
Excellent. So I guess we should mention that we've every month obviously we're going to be doing this, and we've got quite a few that are going to be going in for next year as well. So December is going to be nano-precise condition monitoring. January, I believe, is it's slipping my mind now.
Torque meters.
Torque meters.
Yeah.
So that'll be a different topic as well. So very good.
Yeah, February will be something from Burkhardt.
Oh.
Excellent. So anyways, I guess we'll sign off if there's no other questions. Thank you very much, and feel free to watch the recordings online. Thanks, everybody. Well, have a good day.
Thank you.
Thank you.
Thanks.
Thanks.